So 7 degree of freedom will be a new model in AxisVM X6, which will be available for purchase as an add-on module for the basic analysis package. The module itself will provide a new type of line element besides the existing 1 degree of freedom truss element, the general 6 degrees of freedom beam element, and besides the rib element. And this 7 degrees of freedom element can also be used in the global modeling and in the global analysis of our structures. The 7th degree of freedom, the additional 7th degree of freedom compared to the 6 degrees of freedom beam elements, 3 translational and 3 rotational degrees of freedom, is the warping. So the 7th degree of freedom is the warping. And this will bring a new internal force beside the existing 3 orthogonal internal forces: normal force, shear force, and the torsion and the flexural moments. And this will be the bimoment. So the representation in internal forces of the warping is the bimoment. We will talk about that later. What the 7 degrees of freedom module will be good for, we especially advise this module for modeling of thin-walled members, generally speaking steel members, where the warping of the cross-section is of high importance in the behavior. Let's take a look on the overview of what warping and how it occurs. So warping occurs when the twisting of a member results in the cross-sections out of plane distortion along the direction of the member's longitudinal axis. And this behavior can be represented with the warping moment or bimoment as a pair of equal and opposite bending moments acting on the flanges. Like in the bottom right picture, you see that this bimoment is represented with the equal and opposite bending moments on the flanges. Members of closed sections, such as hollow sections or circular cross sections, will remain in plane under twisting, but generally all open cross sections are affected with warping. Why it is important? Warping has a significant effect in the in-plane distortion of the cross section if it is restrained, since it severely affects the stress distribution. Fork support, for example, is a type of support which restrains warping. And the other important thing, that warping also has significant effect on the stability behavior. So if the warping is restrained, we will have additional stresses which needs to be taken into consideration. And how restrained warping affects stresses in a member is shown on this example, where we have a beam. On this beam, we have an applied twisting moment at the center, and both ends of the beam are restrained against warping. Checking the beam from top view, you can see that the level of twist changes along the member, and this results in elongation on the edges of the edges. And this elongation induces normal stresses, sigma omega, and this normal stress is compensated by the shear stresses, which is tau omega. The other important effect is in backlink analysis, especially in case of steel members, because steel members are usually relatively slender, and they can undergo various modes of global stability failures, such as flexural, torsional, lateral-torsional buckling, or any interactions of these, since the global buckling forms are most often not pure failure modes. And since the geometric stiffness matrix of the 6 degrees of freedom elements neglects the interaction between the bending and torsion and the effect of axial stress resultant on torsion or the Wagner effect, The traditional 6 degrees of freedom element cannot take into consideration specific modes of backlink failure, such as torsional modes and lateral torsional backlink modes and the interactions, which can be computed using the 7 degrees of freedom element. Another thing we will touch is the end releases. So, like any other internal force, bimoment, the 7 degree of freedom internal force component, is transferred through the members from one end of the member to the beginning of the other member. This translation can be controlled by the warping release, and it has 3 options in Axis. The first is the fixed option. This is the default state, and in this case, translation will be performed just like in the case of any other internal forces. The other option is the free, which means that the warping is not restrained on the end of the beam. Imagine a beam to column connection where only the web of the beam is connected to the column with a connection plate. So the flanges of the beam are free to rotate due to the warping effect. And the other thing is the semi-rigid. So the third option is a semi-rigid setting, with which different kind of joint type behaviors can be represented through a dedicated coefficient, which is WF in Axis. And the mechanical meaning behind this warping transmission coefficient is that certain type of connections show different behavior when they transfer torsion effect from one end of a member to another. In case of a diagonal topology, if we imagine a frame with a diagonal topology of frame corner, the beam, and in this case the beam and the column, is connected through a diagonally placed connection plate. In this case, we can consider the transfer of the warping effect as a complete direct transfer. We will see in the example later that what is the behavior of this kind of joint if it undergoes to warping. The other main topology is the box topology. In this case, the flanges of the beam and the column are elongated to the opposite members' flanges, forming this box type corner zone. And in this case, in this box type topology, the warping transfer can be considered as a complete inverse, and in this case the coefficient for it is -1. And the third option is the box diagonal, and this topology is the combination of the two, so the diagonal and the box type, and it can be considered as a rigid connection for warping. So this was briefly the high-level overview of the function. Let me share my screen with a video showing these functions in action. Okay, so hopefully you are able to see my screen now. Okay, so we will start by defining two beam members from scratch. The first one will be a 6 degrees of freedom, and the second one will be a 7 degrees of freedom element. And 7 degrees of freedom element can be defined by ticking the checkbox on the definition dialog. As you can see, the representation is different. In case of 7 degrees of freedom beam element, the logical axis of the beam is highlighted with a blue line. And as you saw, existing members can be changed to behave as a 7 degrees of freedom element anytime by using the line element modification dialog, so they can be changed on the fly. We will apply some completely rigid warping restraint supports on the ends of the beams, and we will also apply the torsion, a twist for the middle sections. We will generate a mesh by dividing the members to 10 parts, and then we will perform the linear analysis, and we will check the results. So after running the linear analysis, warping will appear with added displacement, and as you can see, the rotation has a quadratic function. And if we check the same for the 6 degrees of freedom, we will see that the rotation is present, but we of course don't have the warping display, the warping result. Stresses will also differ. Oh, sorry, this is the bimoment. So at the middle section, the bimoment has the maximum value, and it degrades as we go to the ends of the beam. Stresses will also differ. In case of 7 degrees of freedom member, normal forces are present, both for minimum and maximum values due to the warping. And also we will have the shear stresses changes, and of course the von Mises stresses. If we check that how these additional stresses are taken into consideration during the design phase, we have to define the design parameters for our members. We will check an elastic design, and we will check the utilizations, the critical utilizations for the member. Yes, we will receive a warning message saying that for I, U, and asymmetric I profiles, the effect of warping torsion is taken into account only for the 7 degrees of freedom beams with a class 4 section. So in case of 6 degrees of freedom, this will be neglected. Opening up the design calculations, you can see that how the bimoment is taken into account for the von Mises stress calculation, and in this case, the result is a 111% utilization. You can see that the effect of bimoment is calculated and taken into consideration when calculating the von Mises stress here. If we neglect this effect by opening up the 6 degrees of freedom element, you see that we have a 20% lower utilization rate due to the fact that the effect of bimoment is not taken into consideration. Next, we will go to the Backlink behavior in case of simple column moments, column models. And the difference between these models, that on the left side, both columns are created using 6 degrees of freedom elements, and on the right side, both columns created with 7 degrees of freedom. On the upper, the two upper columns are only compressed, and the lower ones have a bending moment on them. So if we go to the backlink results, we will see that the first backlink shape is a flexural backlink of the 7 degrees of freedom element. It is a backlink around the weak axis of the member, and we have the same pair of this behavior in the 6 degrees of freedom element. If we're moving on to the next backlink shape, which is mode 4, it is represented on the 7 degrees of freedom column due to bending. And as you can see, it is a lateral torsional backlink mode of the column, and this backlink shape is not represented on the 7 degrees of freedom pair of this model. So as you can see, the section have a torsion effect on it while moving laterally. Moving on to the next backlink shape, it is again a torsional backlink mode, lateral torsional backlink mode with a different overall shape, again on the 7 degrees of freedom column. This is again not represented on the 6 degrees of freedom pair of it. Moving on to the next backlink mode, it is a torsional backlink mode due to compression. This shape is also not represented in the 6 degrees of freedom column due to compression. The next is a flexural backlink mode around the weak axis on the 6 degrees of freedom. This backlink shape of course has its pair on the 7 degrees of freedom column. So this is the same with the exactly same elastic critical load factor. Moving on, we have the 10th mode, as it seems to be a flexural mode, but it has a torsional effect on it on the 7 degrees of freedom moment model. And then at the mode 12, we have the flexural buckling mode around the strong axis. This buckling mode is represented as well on the 6 degrees of freedom model. So as you can see, flexural buckling modes are represented in 6 degrees of freedom moments, 6 degrees of freedom elements, while lateral and torsional buckling modes are neglected in 6 degrees of freedom elements, and they are only represented in the 7 degrees of freedom model. Yes, so we will move on. Yeah, we will check the last buckling shape. So this is the idea behind it. Moving on to the next model which is a steel frame, which has tapered columns and beams. As you can see, they are uniform. They have a uniform offset added, and they have a variable cross section with an I300 and the 500 I sections. We have lateral Y directional supports modeling the purlins, as well as we have loadings applied on the top flange of the beams. These eccentricities will take a crucial role when we are checking the buckling behavior of the structure. So first, if we check on the buckling shapes after running the buckling analysis, we can investigate the effect of our support condition, the effect of our supports. So as you can see, we have an elastic critical load factor of 1.1. Basically, this is the elastic critical load factor, and it means that this load level means that on this load level, our structure will have this kind of stability failure. And of course, if this number is lower, the situation is more dangerous. So the lower the number, the more dangerous the situation is. As you can see, this first backlink shape is a lateral torsional backlink of the beams and columns as well. So the critical parts of the model are currently the columns and the beams. So if we want to introduce modifications on our supporting system of the model, we will have to deal somehow with the beams and the columns. If we check higher elastic critical load factors, we will see similar behavior. So the columns and the beams will still be the critical members. So how we can prevent this behavior? This is what we are going to do next. We will introduce a support at the column, on the column. We will place a y-directional support both on the inner and on the outer flanges of the column. And by this, we will prevent the rotation of the column. And we will see that how this support will change the buckling stability behavior of our frame. So as you can see, the first critical load factor is 1.76, and now the dominant members are the beams, which moves out of the plane. So this is a lateral mode, and this is basically the critical member. As you can see, the columns are no longer critical in this form, in the lowest elastic critical load factor form, due to the newly introduced lateral supports of the flanges of the columns. Checking the rest of the backlink shapes will show similar behavior. In general, the beams are the critical part of the model now. Not only supports can have effect on the backlink behavior, but in this next detour, let's say, we will move the loadings to the bottom flange, and we will check that how the position of the load will have an effect on the backlink behavior. So applying the line loads to the bottom flange, the first backlink mode should have a higher critical load factor. So as you can see, the first relevant backlink mode is 2.1. So basically, it stabilized a bit our structure. Of course, this is just an example. This is not a real scenario. What we will do, what we can do in reality, we will introduce even more lateral supports to the beam, namely lower flange supports to the beam. As you can see, on the tapered sections, we will apply these lateral supports in Y direction. And as you can see, currently, this change in the support topology changed the behavior significantly. It raised the lowest elastic critical load factor up to 2.8. And now in this higher load level, the critical member, it seems to be the column. So this way, this was an example of how realistic modeling can help to get a clearer picture of the stability behavior of our structure. All of the backlink forms were some sort of interactions of pure backlink forms, and these backlink forms would not have been able to compute with 6 degrees of freedom. Moving on to the warping transfer. The warping analysis can be controlled through the beam detailing dialog, and as you can see, we have an EW end release introduced in the new version of Axis, where we have fixed, free, or semi-rigid settings. If we are going with the fixed setting, warping, just like for example bending moments and any other internal forces, will be translated through from one end of the beam to the other. If we apply a free setting, and if we define the beam ends as warping free, that would mean that warping will not be transferred through the columns, and this is what you see on the results in a moment. Yes, so warping, the bimoment is not transferred to the columns. If we want to model the different joint types, so the diagonal and the box type of joints, we will use the semi-rigid option. And by using that, we will have the option to set the WF warping transfer coefficient for this warping release. And first, we will create a restraint modeling the diagonal mode. So the first one on the list. If we have created a plate model where we have applied with two oppositely acting nodal force as modeling the warping effect. And as you can see, if you're running the backlink analysis and creating an animation for it, you will see that this diagonal type of joint transfers the warping, so the beam and the column rotation, they are rotating in the same direction. If we create a box type of joint and introducing the beam moments on the column and performing the backlink analysis, what we will see that the column and the beam are rotating in the opposite direction, and this is the effect what can be taken into account with this warping transfer coefficient. And on the left side of our screen, we will apply this semi-rigid setting accordingly. So first, the left side will use a diagonal setting with a warping transfer coefficient of 1. And on the right side, we will use the box type setting by setting the warping transmission coefficient to -1. So choosing semi-rigid, going into the constraint settings and setting the warping transfer coefficient to -1. As you can see, the transfer of bimoment is changed accordingly, so the signs are changed accordingly to these settings. And running the backlink analysis, you can see that the rotation in diagonal case, the beam and the column rotation is the same. This direction is the same, while on the box type, they are rotating in the different directions. So this is how you can take into account this type of joint topologies. So this was my presentation about the use of the 7 degrees of freedom beam element. And now let's see if we have some questions. Okay, I see no new questions currently. If you will have some, just feel free to type them or email us and we will answer them to our best. Now I will hand over the presentation role to my colleague, Gábor Lengyel, and he will introduce the CFD module introduced in AxisVM X6.